So they want us to integrate the power series of the derivative. Nerdy sentence, huh? But take a derivative, basically. Find out what the derivative is first. This is 1 over 1 plus 4x to the third. And then, because that's the derivative of natural log, then you need to multiply by the derivative of the innermost function. So that's 12x squared. So we can write that as a power series because that almost looks like a geometric series, right? The sum of a geometric series is sum a over 1 minus r. So this is almost 1 minus r here, right? And here's the other part of a geometric series from n equals 0 to infinity. Your starting amount a times a common ratio to the n power. Okay, so what do we need to do? We need... Let me pause. Okay, I think I've got it. So we've got 12x squared that's multiplying to 1 over 1 plus 4x to the third. Another way to rewrite it. So this part looks like the sum of a geometric series. We just need it to be a minus in here. So that's just a matter of using a double negative. This is 1 over 1 minus negative 4x to the third. I guess we could have left that up top. So that would be our a, 12x squared. And then our r is negative 4x to the third. So if you plug that in this series representation, the sum from n equals 0 to infinity, we said our a is 12x squared. I guess I could have left that up top. The r is negative 4x to the third. And then that's the n power. Just remember, if you have a negative in here, the convention is to rewrite it like this. Negative 1 to the n. And then it's 12x squared 4x to the third all to the n power. Same thing, right? This makes the series alternate. Okay, so that's the power series of the derivative. They told us to find the power series of f of x by integrating the terms of the derivative, going term by term here. So to find out each term, you'd plug in n equals 0 to find your first term. So that makes 1. We got 12x squared. Plugging in 0 here, you get 12x squared times 1. So 12x squared when n equals 0. When n equals 1, we've got 4x to the third times 12x to the third. Here we'll keep those separated, and it's a negative, so we'll put a minus. 12x squared times 4x to the third. And then when n equals 2, that's going to make a positive. We got 12x squared. And then this is going to be 4x to the third squared. We'll do one more for good measure. N equals 3. It's going to be a negative because this is going to be negative. We've got 12x squared 4x to the third power. So each of those terms can be simplified algebraically. 4 times 12 is 48x to the fifth. 4 squared is 16, so 16 times 12 is 192. Then this is x to the third squared, so the powers on top of powers multiply. That's x to the 6th times x squared, so it makes x to the 8th. And then over here, we've got 4 to the third. That's 768. Maybe I should have kept it, though. I can rewrite it, though. X to the third, all to the third power makes x to the 9th, so that's x to the 11th. Okay, well, no, let's leave it like that, because now they want, this is, remember, the terms of the derivative. We're trying to find the power series for the original function, so we know how to find an original function from a derivative. We'd integrate term by term, right? So this is x to the third now. So I'm actually going to back up here because look, every one is multiplied by 12. In the end, we're trying to create a power series, so we're going to need to see a pattern. So instead of saying 12 times 4 makes 48, we're going to keep it as 12 times 4. And then over here, this is 12 times 4 squared. And then this would be 12 times 4 to the third. That'll help us with the pattern. Okay, so when we evaluate each antiderivative. We've got 12, and then this is, I'm going to keep this, I know it simplifies, we'll keep this as 12 times 1/3 x to the third. And then this will be 12 times 4 times that 1/6 that needs to happen when we take an antiderivative of this term. And then this is 12 times 4 squared times 1/9 x to the 8th. And then we've got 12 times 4 to the third times x to the 12th. Oh, sorry, this should be x to the 9th. I forgot I was taking an antiderivative. And then the pattern continues. So now we can see patterns in each of these. So we make a sum. We can start it at n equals 1 to infinity because x is always something, is n times 3. If you plug in 1, you get out 3. If you plug in 2, you get out, oh, this should be a 6. I forgot the antiderivative here. Plug in 3, you get out 9. Plug in 4, you get out 12. So that takes care of all the x's. Every term is being multiplied by 12, so we'll put a 12 in there. We've got 1/3, 1/6, 1/9, so we're multiplying this by 1 over 3n. And what else do we need? We need these 4s. We got 4 to the n minus 1 power. Because this is 4 to the 0, 4 to 1, 4 to the second, 4 to the third. And I think that's everything. Oh, I forgot that we're alternating too. So we need to also multiply by -1 to the nth plus 1 power. It's n plus 1 because this leading term is positive. So if you plug in 1 in here, that makes it positive. Okay, so I think that's everything. If you type that in Knewton, that should work. That should work. I'm just wondering if Knewton would want a different representation. Let me check off screen here. Newton actually starts at n equals 0, so we can back it up. Is that what that question says? Because I'm wondering how would students know. It does say. In the question it says n starts at 0. So we can do that. We just need to go back through the terms again. We need x to the 3n plus 1 power. Because now if you plug in 0, oh no, sorry, it needs to be plus 3. Because if you plug in 0, 3 times 0 is 3. This is 0. 0 plus 3 makes 3. So that takes care of all the x powers. Every term is being multiplied by 12, so took care of that. We've got the 1/3, 1/6, 1/9 happening, so that's 1 over 3n, but this needs to be plus 3. Because if I didn't do that, n equals 0 would give us a 1 divided by 0 problem, right? And then 4 to the n minus 1, we can actually just start that as 4 to the nth now, because if you plug in 0, you get out 4 to the 0, which is what we're supposed to have for the first term. And then it still needs to alternate, except now that we're starting at 0, we're going to have n. So 2 different ways of writing it as a series. This is the one that Knewton was looking for.